Hello and welcome to 15th lecture of course on corrosion, environmental degradation and surface engineering. This is the third lecture, environmental assisted surface deterioration or degradation. First two slides of this lecture I will be trying to summarize what we have learned in earlier two lectures. Lecture 16 will be on testing kind of thing, maybe what are the different testing methods available, because we know there are number of standards available to us, so that there should be uniformity of presenting the results. So, we will be starting from that portion from lecture 16. So, probably this is the last lecture of the environmental assisted surface degradation. As I said that we will be first two slide I will be trying to cover or maybe highlight what important lessons we have learned from earlier two lectures. Now, we said very clearly that corrosion basically enhances the degradation phenomena. What is the reason? It causes the material to become brittle and fracture more easily. So, even there is a wear debris which was supposed to have a lot of plastic built up, and maybe say the non-dimensional wear coefficient must be very high, 10⁻⁷ or very low, sorry, 10⁻⁷ or 10⁻⁻10 or 10⁻⁵. What corrosion does, it reduces, or we say that in fact it increases the value in a manner that wear coefficient becomes on a higher side, and then we are not able to find that life cycle which we were able to get without corrosion. So, that is why we written clearly the corrosion causes the materials to form or to become a brittle and fracture more easily. It can be completely disintegration of the product or maybe the chipping of the wear debris from a surface. Now, this is what I mentioned clearly earlier, the process for the creating wear debris from high cycle fatigue. So, in normal condition when there is no corrosion available, and then and the very good environment conditions are there, then there is a possibility that every wear debris will be getting separated after maybe say 1 million cycle, 10 million cycles. So, it is more like a high cycle fatigue phenomena. While coming to the corrosion, it will convert this process to low cycle fatigue. Now, maybe after 100 cycle wear debris will come out, 1000 cycle wear debris will come out. So, that is something like a low cycle fatigue process. Now, it is more like a multiplication factor. Now, when the corrosion happens, it really allows easy removal from a surface. When the new surface gets exposure, again it is a much more chemical active and the further corrosion will occur. So, these two processes like a wear, fracture are getting associated with corrosion, and all three together will work with each other, and maybe there will be kind of a fatal the failure or the damage to the surface. Now, that is what has been written here. By exposing new surface to corrosive environment is happening automatically, because there is a wear phenomena or wear is getting associated with a fracture phenomena, and there is a removal of the debris from a surface. Naturally, when the debris gets removed from a surface, a new surface will get exposure to the environment and that will get corroded. So, this phenomena really increases the wear rate. That is what we say, that by exposing new surface to corrosive environment, wear method remove corrosive product can speed up the corrosion and causes a corrosion byproduct. Now, another thing is coming, where the debris will go. When the surface is getting degraded, then naturally the particles are coming out of the surface, and those are, we are using a word here, this can be treated as the corrosion byproducts. That because of the corrosion and associated wear, and then now we have byproduct, the particles, and those particles can act as abrasive particles. That is why we say the wear coefficient maybe in normal condition it was 10⁻⁻, maybe say 9. And then when we say that corrosion and wear get associated with each other, then it turns out to be 10⁻⁶, and then when the corrosion, wear and fracture get associated with each other, quite possible the wear coefficient may come down to the 10⁻³ or maybe say increases value and then to the 0.001 instead of 10 raised to minus 9. So, these are associated with each other. That is why we say that these phenomena are important to understand, and in our earlier lecture we have described those phenomena. Now, one more parameter is something like a friction, and then whenever there is a friction between the two surfaces or at the interface, we need to apply a pull force or tangential loading, so that one surface moves related to other, and we know because of the friction and this energy will be consumed and it will be getting converted to heat. So, the friction phenomena or tangential load which is really required to rotate or to slide surfaces, that will also add a stress level, and that increases the we say that shear stress, and because of that more and more surface damage occurs. So, if more and higher friction force and more possibility of surface damage, if there is a lesser friction, insignificant friction, quite possible there will be a sign of the subsurface cracks. It may take little longer time to come to the surface. If there is a high friction, the possibility is that those cracks immediately come to the surface and then debris will be removed, and more and the debris will get generated because there will be corrosion and related phenomena. So, I can say here that tangential loading can aggravate degrading effect related to wear, corrosion and fracture. So, these three phenomena plus friction force. So, in all together if we consider, if we are able to model it properly, I can say that then we will be able to really design very good product which will be lasting a lot, and it will be having very high serviceability, and it really reduces overall degradation of environment also. As in my earlier lecture I mentioned that surface gets degraded because of the exposure to the environment. Now, because the product is completely damaged, naturally then it has to be, it can be treated as a waste material, and that waste material will again cause a degradation of environment. So, there is a two-way process. If we are able to really bring a surface engineering in between environment and the product, that we can really avoid or minimize the degradation of surface, and say it is also related to the environment reduction, the degradation of environment also. So, there we will be doing both the ways by bringing a surface engineering in this at the interface. So, this has been mentioned and we have already covered. I am trying to just summarize on this. Now, what is a major issue, because in previous lecture we have covered couple of case studies, and then we say the corrosion plays a very important role, particularly the crevice corrosion, pitting corrosion. Reason being, we do not know where is a crack and how the chemical is really infiltrating into the surface and making some sort of hidden electrochemical cells. That is what we say, recognizing, understanding, finding hidden electrochemical cells in engineering a structure. Like the way in the previous lecture we have covered something, the bridges. So, those bridges are having a number of electrochemical cells. If we can really prevent those, then the life will be very better, maybe much better, or maybe say that the life of the product will be like high cycle fatigue, or otherwise because of the corrosion, because of the hidden electrochemical cell, the life will come down or maybe will be reduced and it will become a low cycle fatigue. So, this is what I mentioned here, recognizing hidden electrochemical cells in engineering structure is essential. So, if I do not have understanding, if I am not able to understand how the electrochemical cell is getting formed into the surface or maybe say just below the surface, I will not be able to suggest the surface engineering tools, or I will not be able to prevent the corrosion phenomena. So, this is important, and that is why we say that to prevent collapse of the structure or maybe say the damage or rupture of the structure, we need to also account, if we understand how much corrosion will occur and what is the really relation with the time. Maybe the initially I am taking some factor as a 1, and over the time this factor is reduced. So, can I really do multiply that factor or corrosion related factor with the strength of the material, and I say yeah, maybe at the beginning the strength is something like 100%, After maybe say 5 years, the strength will be 90%, after 10 years it will be strength will be 80%, and then there will be some sort of line available, or we say the threshold available. Now, below this line we should not use equipment, we should disintegrate complete the bridge or complete shape or complete plane and then come up with a totally new system. So, that can be what you say that, and the life can be analyzed when we have those factors available, when we have understanding of those systems also. So, that is why I say to prevent collapse of the structure, consider decrease in strength of a structure component exposed to corrosive environment. So, this is important, that is why we have been covering these topics. We also explored maybe say something on a satellite which are operating in a low earth orbit, that is what we call a LEO satellite. And then we also learned maybe the covering 2 papers, they use the protective coating, and that protective coating particularly for temperature control coating. Another one we explained something like a atomic oxygen resistant coating, so that damage to the surface is minimum and the temperature does not go beyond certain limit, and then whole satellite can be controlled operating level of the temperature, or maybe the temperature is kept well within the range, so that our complete control system is functioning properly. So, this is what was mentioned in earlier 2 lecture. We say that these kind of coatings are required to reduce the surface deterioration, degradation, and then for the orbits which are really working in a low earth orbit. As I mentioned in the earlier lecture, in a low earth orbit we have many pollutant more than like even as I say that atomic oxygen is one of the major thrust. Other thing I mentioned that satellite need to have very high speed, and the high speed naturally, and when we were discussing about the Titanic case, we say that because of the high speed 22 knot speed of the ship and is striking at a very big the iceberg, naturally damage will be very high. Maybe say that the sensitivity of the velocity is very high in this situation. So, when the vehicle is operating such a high speed, naturally we need to really take care appropriately, we need to have a complete understanding, and we need to suggest a better coating. And that is why in both the cases we found that the researcher have suggested the nano coating, because if you increase even the weight of the materials, that is also going to cause another problem. So, we do not want to go to that. How small or infinitely small coating can be used, that to be a completely well distributed without any fault, without any delamination, without any bubbles inside. So, those coatings are really required. So, we really require sophisticated technologies for solving this problem. So, this is what we have covered. Now, we have a second slide which also highlighted what we have covered earlier. So, here we also say that environmental variables which are really causing the surface damage, and then as I mentioned that there is a coupling between the wear, corrosion and fracture. These are 3 mechanisms work together and then cause a major problem. So, now I am trying to connect sequentially something like that. Say that wear degradation results in scratches, pitting and grooves, or maybe other kind of the defect. So, wear is creating problem like this on the surface. There may be also fabrication related problems, but because of the deformation, because of some other process, or because of the relative sliding, this kind of scratches or pitting or maybe grooves can be cut on the surface. Now, once those are there, then the major role is played by the corrosion. We say corrosion takes advantage of these voids or whatever the deformation or pits on the grooves, and then allows to generate a electrochemical cell there. Now, when it is getting this crack and the electrochemical cell is formed on those surfaces, then what will happen, that it will allow maybe say assist the crack to get propagated, and when there is an assistant to propagate the crack, naturally fracture will occur, and that is what we say that then because of the fracture it will get divided, maybe this process will divide the surface into 2 or more segments, and that whole process is known as the fracturing process. So, wear, corrosion, fracture, they are working in a sequential manner in this form. It may be slightly different, but I thought maybe this is the best way to present that how these are linked with each other, how they amplify each other, and then what are the really the factors. We say we have learned that the chemicals water, humidity, we use the word. Acidic form, or we say pH value lesser than 7 will be important. Increase in a temperature, increase in a heat is really going to increase the wear rate. If there are crevices or maybe say the joints, as I mentioned in the case of the bridge, that if there is a joint, naturally there is a problem, because most of the time we follow the fabrication process, we really do not measure each and everything properly, and there will be some sort of crevices, there will be some sort of gaps are sufficient for the corrosion to take place, or maybe say the electrochemical form the cell to form there. Now, how severely that can act, it depends on the different environments, but joints is also a major issue. So, if I can really develop a product without any joint, that will be the best. But again, as I mentioned, the fabrication cost will be phenomenal, and then we need to work also that it should be cost effective. Of course, not for the aircraft, those are the system where the cost does not really matter that much, but other things matter a lot. If there is a casualty, what will happen? So, that the socio-economic effect that plays a major importance there. Right. So, in this case, another one I may also mention, there are some sort of pollutant, contaminants, all this will affect. These are all related to atmosphere, environment. So, everything together really they affect surface degradation. Now, because of the surface degradation, what will happen? Sometime we find that the chipping is happening at a much faster rate, so size is different. Sometime we find the shape is broken in number of, maybe the system is broken in number of parts. So, the shape is also changing significantly, or another one, even everything is a mild level, but overall efficiency which we really require something 95%, we know we are not getting. So, that product is useless for us. That is what we say, maybe we require some sort of Newton meter, some torque x, and I am not getting x torque. Naturally, I know that motor cannot be rotated, other units cannot be operated. So, we are losing our the important function of valuable features, and then there is no point to continue the product, we need to replace, even though it has not failed or maybe it has not fractured in the multiple parts as such, but it has a loss its ability to perform the valuable features or to show the valuable feature. Now, so that is what based on this we say that machine aging is affected by surrounding, or we say atmosphere, and then I can say the failure as I mentioned that it may not be only the fracture, failure happens when the efficiency goes below a specific limit. As I mentioned, the 95%, maybe sometimes is a 90%, maybe 85%, whatever. So, that if there is a specified value has been defined, and then we are not able to get that kind of efficiency for a product, actually the product has a failed. So, failure does not mean the breaking in the parts, many parts. Breaking and the failure may also that something that it is not really showing the performance what was expected from the product. Now, we say that another surfaces can be protected from a wear, corrosion, fracture using nano coating. Of course, so micro coating is also there, but now in latest technology we are talking something like a nano coating, and the coating thickness should not be beyond certain limit, and quite possible after the removal of that we should come up with some refabrication or maybe say reconditioning of the products. So, and particularly when we were discussing a LEO satellite, we say nano coating is really helping. So, this phenomena, so wear, corrosion, fracture can be controlled by using the nano coating. Now, nano coating can be crystalline or non-crystalline. Is a nano crystalline deposit. What will happen? It will increase the hardness of the surface. So, wear rate reduces, and then that is why the wear rate comes down, and then wear rate is coming down, and then there is a possibility to prevent the corrosive or chemical attack on that, and there is a possibility to reduce the fracture. And now, in addition, if the nano coating have a low friction, actually the most of the things will be subsurface, it will not come to the surface, and it will not give exposure of the new surface to the corrosive environment. So, the life will be extended. So, this is what we say that they help to mitigate corrosion by passivating the surfaces and isolating the contacting bodies. So, this layer or surface engineering layer comes between the product and environment, and that is why we use that this is the latest technologies related. The nano coatings are important to understand, and we will be covering in details some coatings when we start a lecture on the coating or surface engineering. So, we can say that coating and surface modifications are the common tool, or maybe say more useful tools in a surface engineering. And when we discuss the topic on the surface engineering, we will come back or we will return back to these topics. Now, another thing is that when a major metal part, this is just like a brainstorming related, we say when the phenomena are happening, we have a better understanding of those phenomena, then why not go ahead with this kind of thing. We say there is a big metal structure, and we in previous lecture we said there will be some life, maybe 20 years, 25 years, 30 years. So, example take example of the ship. Suppose I design a ship for 25 years, and after 25 years we need to really dismantle the ship, or maybe we have already learned that many times the big units are dismantled and then given to the further processing, so that they can be remelted and can be reused somewhere. But so that requires a lot of efforts. Now, we say that instead of that, if I know how to chemically degrade the product, and that too in a valve within a time, maybe say 10 hours, 15 hours, 20 hours, then why not we design that? So, whatever there is a negative effect of a corrosion, why not I utilize that science to make it a productive manner or to be utilized in an effective manner. That is why it has been given when a major metal structure like a ship reaches end of its life, is to sustain its own life, useful life, it will be economically beneficial. I am using the word, it will be economically beneficial to use a science to really disintegrate this complete product. And that is why I say it could be programmed for the self destruction. If the product can be self destructed, I give an exposure, that whatever we are saying, we should not give an atmospheric exposure, but there is some product and which we need to really demolish or maybe separated in various parts. So, why not we go with a corrosive environment for the self destruction of the units, and so that is more manageable part, or maybe that we can really divide in a complete system in the many parts, and then we also do in recent practice. There is the current practice in most of the nation including India is the dismantling of the old ship by manual work, by engaging the labor or engaging the low cost labor. But why do we really require when we have a scientific solutions available, and that will give the solution that will give result in much faster pace, and then it will be also useful that whatever the product we are getting and the way whichever subsection which are in a really in functional form, we can do a reconditioning function, and then the components which are not in a form can be removed and maybe remelted and reused. So, this is what I believe, that when we understand the science, we can best utilize that science for the productive manner. It is not only to avoid the corrosion, to avoid the failure, but wherever failure is required, why not I use this science, why not I use this kind of a modeling to get the max benefit or the major benefit from that. Now, let us start today's lecture with a few other aspects or other factors. We know that ozone, or maybe a number of times we have heard the ozone is harmful. The question comes, how ozone plays a role to degrade the surface. So, that is why this topic says surface degradation due to ozone. And what is really ozone? We say mostly then ozone comes in a natural environment, in earth environment. However, we know also that there are a number of activities done by the human being, which really like a number of industrial processes kind of pollution, which also releases the ozone. Ozone is like a very active element of oxygen. So, that is why we use the word as basically the O3. They are highly reactive gases, and then they, because of the very high chemical activity, what will happen, they will go through sequence of the chemical reactions, and then there is a possibility that whole molecular structure gets damaged because of the ozone. And then we know very well whenever there is some sort of carbon material or organic material, ozone plays a very high damaging role to those components. So, that is what we are trying to explain in the remaining of the portion of this slide. We say that the ozone really follows a cyclic mechanism of the degradation process. So, it is a chain reaction, it is not immediately one and then it is not maybe the one movement only, but it will continue. And how it continues, we say ozone molecule react with a double bond, particularly of the material which have a carbon or maybe say organic polymer chain, because they will have mostly the double bond, and wherever there is a double bond, the oxygen plays important role because of it is high chemical reactivity, and then the bond will become a single bond, and then because of this reaction what will happen, there will be creation of the functional group. So, now molecule comes in a form, it increases the chemical activity, and not only the disintegrate of the one bond, but it becomes a much more reactive than, and then in this way say the oxygen containing functional group, like even inside the polymer structure, what will happen, this the functional groups make subsequent reactions also, and still ozone is also there, the oxygen is also there. So, that is why there is a chain reaction, continuous reaction will be there, and then it will speed up the degradation process. And we know very well the organic materials like a rubber, plastic, and then a number of paints also, they degrade because of the ozone, because of the exposure to the ozone. That is why we say these materials are very vulnerable to ozone induced surface degradation. Now, I am just trying to explain only on based on the ozone, and then the one of the material like a rubber, we say what happens in the rubber case, we say ozone is so reactive, it makes a number of cracks, or we say network of the cracks. So, instead of a pieces getting fractured in two pieces, it really develops so many cracks, disintegration happens very fast, and that is why we say that this is what we in the terminology use like a ozone cracking. And of course, we say ozone cracking, crazing, surface degradation, loss of the flexibility because of the and then the lack of a network which is available, or maybe connectivity is there, the kind of the rubber which has a very high elasticity, and maybe say it has a high loss modulus, but because of the number of cracks which really gets developed on the rubber material, it loses completely flexibility, and then the strength is almost negligible after exposure to the ozone, and that is what we say that is a classical symptom of the ozone laid degradation. So, what are the symptoms is the cracking, crazing, surface degradation, loss of flexibility, and then there is a continuous decrease in strength. So, if these are the features available, we need to really figure out what has happened, from where the ozone is coming, and then we can do a chemical analysis of those damaged surfaces, the way we have learned in our previous lectures. So, whenever there is a degradation damage, we go ahead with some sort of an analysis, or maybe say SEM analysis or EDX analysis, and we try to figure out what has happened to the surface, so that we can prevent further damage, or maybe say in the future damage, or we can upgrade the product, or maybe change the material which is really required. Now, another point comes, if the concentration of ozone increases or temperature increases, or another one is that longer exposure of time, then the degradation will be much higher side. So, there are three factors: concentration of ozone, if increase the concentration, more and more damage; increase temperature, more and more damage; increase the time to exposure, more and more damage. So, this is related to ozone. Now, and then there is a one case study available in literature, maybe many more, but I have just picked up one case study which was published in 2022, and we say that what they have done, they use the word alkali lignin. This alkali lignin that has been given the nomenclature Al contains a carbon, and then it was really subjected to the ozone. How it was subjected to ozone? They use a ozone generator, and then these are available in the market, ozone generator, in a cost effective manner, and then many times we really require oxidation, we really require cleaning of the water. Those things will be available, not difficult to find. So, they give exposure of the ozone 85 milligram per liter, and then they maintain something like a 3 liter per minute of flow rate of that, and then exposure was also 45 minutes. So, here the concentration is being given, and then I think the temperature was kept somewhere around 45 degree, and maybe I have not mentioned on this slide. And another thing is that they compare by the subjecting the pH level 3, 7 and 12. So, based on that, and then they try to figure out what is really happening. So, AL no exposure of the ozone. OL pH 3 is a exposure to the exposure of lignin to the ozone. That is why the ozonated lignin is something like OL, and then environment is something like acidic pH 3, then pH 7 and then pH 12. So, these are the three environment, and then they try to figure out what is really happening with the material. And you can see here the AL when in the without any exposure to the ozone looks very clean surface, maybe one or two places, particularly is 1 micron. So, we are able to find out some sort of debris on the surface. Now, coming to the pH 3, you can find out the very big dip there, and that is why we say that it is not only the increasing the surface roughness is one point, but there is a really big deformation of the surface also, and then there is a many cracks also. You are able to see the cracks over here, cracks over here, and it has happened because of ozonation, and then the laser pH the pH value. Now, if the pH value is increased, then in this case particularly pH has been kept as a 7. In this situation you can see the deformation is much lesser. So, even the neutral environment pH 7 what we were showing in the acidic environment, now even the neutral environment ozone is really acting on that. So, it is not only the chemical, but basically the major damage is happening because of the ozone. You are able to find out that there are number of debris, more cracks, or maybe the brittle fracture kind of thing. Well, even coming to the basic nature, alkali nature, that also that we are able to find out the faults or maybe the surface damage. Of course, if I compare naturally, I will say that this is the original surface, least damage will happen when there is a alkali nature, or maybe environment is alkali, or maybe the basic nature. While coming to neutral, there will be some damage, and then coming to acidic, there will be severe damage. So, ozone naturally in presence of the corrosive environment or acidic environment will really be affecting surface majorly. So, we should avoid this kind of exposure, and that is what we say that ozone really damages, and in this case we are comparing that ozone in presence of acidic environment damages much more compared to the neutral environment or basic environment. And then we are trying to cover the second case study, which is available and we have picked up in from even journal 2019, was published in 2019, and then fortunately this topic has been covered in when we were covering the corrosion topic, and we say crevice corrosion or crevice corrosion is important. We say that people say the localized corrosion, and we say no, instead of going for localized corrosion, we should divide into pitting corrosion and crevice corrosion. So, this case study is basically related to crevice corrosion, and then we say that what will be the effect of crevice corrosion on a stainless steel, and then the grade is something like 304L stainless steel grade. And then what is really from where the chlorine comes, so we know that near marine environment or near coastal areas chemical then the chloride will have a more tendency, or maybe the chloride ions will be more in number compared to the normal environment. So, what we say, the surface degradation caused by chloride is a major concern, particularly in a coastal location, or as I say the marine location, or maybe some industry or some where the chlorides are really pollutant, or the pollution level due to chlorine is on a higher side. So, maybe even HCl factories, or maybe where it has been formed, there is some sort of byproduct also. So, chloride ion, one of the important thing is chloride ion is that they have much higher capacity or much more chemical activity. So, if there is some sort of surface on the steel, obviously the contamination layer which has been made because of the oxide, and we generally get happiness, yes, because there is an oxide layer, the steel surface or and then this material surface will be protected, and an oxide layer will act as a protection layer on that. But chloride, in the presence of chloride, the protective layer gets ruptured not rupture, I use a word, maybe some sort of crevices will be formed. So, chloride ions are easily able to penetrate that protective oxide layer. So, from top I will be thinking, oh, there is a good oxide layer, but because of the crevices very small, maybe say miniature dimension, chloride will pass from that surface, and when it will directly go to attack the metal surface, they will replace that in form of the metal chlorides, and then metal chloride having a very we say that is basically corrosion. So, it is not a protection. After that, it is really complete system is changing from a protective environment to the corrosive environment. Naturally, the damage will be very high, and then it is we need to consider from that point of view, and that is why you say that this chloride produce a pitting corrosion or crevice corrosion. So, crevice corrosion is also important, pitting corrosion also maybe depends on the material and situation and additional circumstances and or maybe location, that things will change. Now, it is not only the metal, literature says that even the concrete, where there is a steel bar or the steel reinforcement, and then there is a top of there is a concrete layer, or maybe the cement layer, or maybe the cement sand layer. But chloride ion having so high infiltration rate, it will really infiltrate concrete cover also and directly reach to the embedded steel reinforcement, and that is why the terminology is used something like this is a chloride induced reinforced corrosion. So, there is a separate topic we call a chlorine induced reinforced corrosion also. It really goes and attack the steel reinforced and then really weaken the material. We know when it weakens the material, naturally the integrity of the structure will be in a doubt or will be in a problem, and we need to really take proper care to avoid this kind of failures. Now, in this case study particularly which has been covered in this reference, they studied on SS material, and then they use canister as a kind of the barrier, particularly for nuclear fuel, which is the material spent fuel, nuclear fuel, and then they want to cover and provide a better protective coating, so that exposure of this nuclear fuel should not be there to the environment. So, that is why they use SS canister, and then however, they found that this kind of canister or this kind of material is subjected to localized corrosion, that is what we call a pitting corrosion or crevice corrosion, and then that particularly in a sea environment where there is a more chances of chemical ions. So, that has been reported, and this paper tried to figure out what will be the effect of this kind of corrosion. Of course, chemical the composition of 304 stainless steel has been given, very low percentage of carbon, relatively high percent of silicon, and then chromium has been kept very high, nickel has been kept very high, manganese has been kept also very high. So, in this case is a really good material, or we say that it should have a good chemical resistance, but unfortunately because of the phenomena or because of the chloride ion environment, it fails, and that is a major issue. So, they did an experiment, and then to find out the real impact of the chloride attack on this material. So, they use sort of the smoothing of the specimen, because there are some standards how to conduct these experiments. As I say that we will be covering in the next lecture how to perform the test, what are the different methods available. So, as per those standards, the surface should be uniformly polished whatever the sample they were choosing, and this topic also has been covered in our earlier lecture which was delivered on the corrosion. So, they use this one, and then they use M6 bolt, and then kind of polymers which really allows to form the crevice corrosion and then allow the infiltration, and then they also maintain the torque value which as per the standard they kept as 1.13 Newton meter to create a complete sample, and so that it gets subjected to corrosion phenomena, and then using the electrolyte maybe based on the sea water, and then they synthesize seawater also, that is as per the standard which has been also mentioned, ASTM D1144198, and they use NCL 94 and then NCL 58.5% and other composition as per this standards. So, they follow the norms, and now in this slide particularly we are representing the results. So, what are the results? This has already been covered in our previous lecture, how to form the specimen, how to get connected, and finally, this unit will be subjected to the corrosion in an environment, and those units were also shown in our previous lecture. So, this is what Albin discussed. They kept a temperature around 45 degree even in a marine environment. Now, they tested three things. One, then they kept the concentration very low, something like a 0.1 gram per meter cube. Then they tested it for around 5000 hours, and then you can see this is for 45% humidity, this is for 55% humidity, and this is a 70% humidity, and this is when showing this result shows when there is a 45%, I am able to see more damage of the surface. When the humidity increases to 55%, I find least damage, again 70% there is an increase in the damage of the surface. When look at the microstructure which is getting connected, in this case that we are able to see that there is a more damage here, least damage, and maybe say mid level damage in this case. So, this paper maybe the study what author wanted to convey is something like there is a perfect combination. Now, perfect combination of humidity and percentage of the chloride. In this case, like they use a 0.1 gram per meter cube, and we are able to find the more damage at the 45 degree, minimum damage at the 55 degree, and significant damage at the 70 degree. However, when they increase this percentage to 1 gram per meter square, and then they found even the damage is a more like starting from 45% onward. So, it depends what kind of combination we are using, what is the humidity level, and what is the percentage, and overall chemical reactions are important. So, if you are able to model those chemical reactions and able to simulate, we will be able to really figure out how much damage will to happen to surface. Again, we cannot remove complete damage, we can minimize the damage by understanding science, by understanding the mechanism, by doing a simulation modeling on this kind of components or this kind of process. So, that is why we can say here that due to low chloride concentration, as I say 0.1 gram per meter square, a more humid environment is required. So, that is why I say 70% humidity is very essential in this case, may be required to transport, to filter, to infiltrate the chloride into the crevices also. So, this is important, as I say that the humidity and percentage of the chlorides are together, we work together, and then maybe if I increase it, they kept a temperature constant 45 degree, but if I increase the temperature to 70 degree, results will be slightly different. So, that is why we cannot do so many experiments. So, that is why we really require some sort of testing, and that is why we say that we will be covering those kind of testing in our next lecture onward. Now, there is another study, something like a sulfuric acid. And earlier one of my lecture I mentioned that even when sulfuric acid concentration is very high, it may not harm the product that much. Of course, it can harm the human body, but it cannot harm the product as such. Many times to make electrochemical reaction, they really require water, or maybe say require appropriate electrolytes. So, in this case study, authors they try to compare sulfuric acid with citric acid. Citric acid is one of the very common acid available, and then mostly we use also in the food industry. So, this is what they have done. First thing is that from where the this sulfuric acid comes into environment or atmosphere, we say in this case atmospheric sulfuric acid is generated, formed by when the sulfur dioxide as one of the we say that pollutant or which gets released from various sources is emitted from because of industrial activity, and then maybe as we are using the word combustion of our fuel, maybe more automobiles are responsible for this kind of the pollution. when it gets mixed with the water, oxygen and other molecules in environment, then S2SO4 is formed, and then it really have a acidic nature. So, as in another earlier study we say when ozone gets very impacts severely when there is a presence of acid. So, mostly acidic circumstances increase the problem, and particularly in this case acidic circumstances or environment, they solve and then make the aluminum soluble into the soil. So, they wanted to check this kind of thing, what is the activity, how the aluminum will get dissolved completely into the S2SO4, and then that material goes into the soil. It will naturally cause a hazardous to the plants. So, it is very difficult to separate, but if we know the circumstances, we know the what is really happening, necessary actions can be taken place on this. So, in this study they use aluminum alloy 6061, and then they use some sort of electrolyte in the sulfuric acid, and of course, in this case the 4 solution they have used. Sa is a sulfuric acid, Ca is a citric acid. So, A has been given sulfuric acid with a current density something like a 1 ampere per centimeter square. B has been used a higher current density 7.2. So, this is a 1, this is a 7.2, and they showed if now even the same concentration, same operating temperature, same time, if I am using the current density or increasing on a higher side, it is really affecting. So, 7.2 is really causing a more damage, and fortunately or unfortunately citric acid is showing a more dominating factor compared to the sulfuric acid. So, it is a where we assume the sulfuric acid really will act much more severely, but in this case we are able to find more damage because of the citric acid, and that is why and of course, in both the cases the B and D we find that the higher current density is really creating more porosity and superficial cracking, and of course, in my thinking that the citric acid is really affecting more, which is one of the very commonly available acid in our in the food industry also. So, this is an important consideration when we assume in environment, outside environment sulfuric acid, inside environment maybe citric acid, and then we need to really think what will happen to different chemicals which we are using, and then maybe say even polymer which we are using, and how really it will affect the health, human health as such. So, this is has been mentioned by, and now finally I am trying to come up with another important topic which has been also covered in corrosion topic, but now trying to summarize in this lecture, which has a much more impact compared to other kind of chemical activities. So, hydrogen embrittlement, which is now becoming a very important, and we need to really consider, because we find very difficult to resist this kind of embrittlement. And what is a hydrogen embrittlement? We have covered, but I am trying to summarize again. We say it is generally triggered by atomic hydrogen, and it causes maybe reduces the strength significantly. The way we have seen rubber material, it gets cracked in a number of pieces, or maybe there are network of the cracks, and then in presence of ozone it disintegrates in number of pieces, it loses the complete flexibility. So, rubber material becomes kind of no rubber, maybe kind of no elasticity, no the damping kind of properties. So, same thing in this case, most of the metals they lose the most of the property because of the hydrogen embrittlement, and then they cause an unexpected fracture. That is why this is very important to consider. Now, another thing, this phenomena is now common in aerospace industry, oil and gas industry, automotive industry, power. So, whatever the main important industries, hydrogen embrittlement becoming the common in those kind of structure, and it causes really the damage to a structural element, and then associate risk for the human life, because these all the major units, and then human lives are one way or another way related to those units. So, really cause a more damage to the human life also, and of course, product gets disintegrated, and then maybe associated oil, or maybe associated fire, or maybe associated some sort of debris comes in a million pieces. Naturally, it will really be affecting the environment. and we see very clearly the hydrogen embrittlement really and then accelerate the surface degradation, and even many times the stress level is very low, still the failure happens. So, that is why this mechanism becomes a very important. Now, what from where the hydrogen atom comes? We say that it is a very common in a corrosion, like even water, iron and water reaction or rusting form, we find the water gets disintegrated hydrogen ion and OH ion, and hydrogen is free. It can really penetrate to the surface inside, and then if it remain unbalanced, of course if we have a balancing procedure, we can do we can really make a good process, but we do not have, then quite possible this the free atom or hydrogen can really atomic hydrogen can penetrate into the surface. So, it comes in during corrosion, electroplating, and sometimes there is a exposure of the hydrogen, or maybe hydrogen enriched environment is there, hydrogen rich environment where the product is really kept for the longer time. So, in this situation what will happen, this atomic hydrogen will infiltrate through the substance, and then major problem, it will enter to the lattice structure of a metal and get closer to the grain boundaries. Now, grain boundaries are already weak planes. We know that even the corrosion will affect the grain boundaries, but here the hydrogen is really getting clustered around the grain boundaries. Naturally, the damage will be more and more. This becomes a more like a microstructural defects, and that is why there is a possibility of the abrupt fracture. And my previous lecture I say the corrosion takes little longer time, but somewhat hydrogen embrittlement is slightly faster than the normal corrosion. That is why it really requires more attention in the present, and I say that it is very important for a number of industries also, which are directly or indirectly related to the hydrogen one way or another way. So, this is what we say, it really go ahead with the hydrogen induced cracks, and then even the expansion of crack or propagation of crack is also very fast. So, that is why it is become a very important, and just this portion has been written to give again the exposure, say because hydrogen is frequently created during corrosion reaction. That is why many times people believe that hydrogen embrittlement itself is a part of corrosion. Again, in my view, corrosion is not that fast as a hydrogen embrittlement. So, keeping many times a separate category really gives a more important or more focus that we need to really avoid hydrogen embrittlement. And then in the one of the common reaction we see corrosion of iron in water results in reduction of hydrogen ions, maybe say hydrogen ion OH and then the forms in this situation, and that we can allow the hydrogen embrittlement. Another similar thing which has been mentioned, hydrogen atoms diffuse through material and condense the internal imperfections, that the imperfections may be a crack, it can be a grain boundary. So, it will really look at the weak planes, and we know that crack look also the weak planes, but this has a much more impact compared to the simple corrosion, or wherever there is a disintegration or the discontinuity or imperfection, this will cause a major problem. So, we need to avoid it, we should avoid, otherwise the loss of stress will be loss of the strength will be very high, and maybe the material will break at a much lesser stress compared to the design stress. That is why we say that we should avoid as much as possible. We should really model hydrogen embrittlement in proper way, and then we say yeah, we really require another solution to avoid the hydrogen embrittlement, and it has happened to the number of units also, and maybe when we try to cover surface engineering, we will cover the few case studies related to that. Now, in one case study, and then in one of my previous lecture also mentioned, because of the corrosion, even the fatigue process, high cycle fatigue becomes a low cycle fatigue. Even the mode changes from a ductile mode to complete fracture mode, the brittle failure, and that has been shown in this slide here. We say effect of hydrogen in changing fracture morphology and failure mode. Fatigue failure mode itself gets changed from high cycle life to the low cycle life, and then in both the figures we are showing the post necking, that means the fracture has happened to the surface, and then we are showing that final surface. You can see this is still a cone, cone and cup kind of a shape. There is a cup in this case, other portion will be having a cone, while in this case we do not find that, and this has a subjected to hydrogen embrittlement. So, this has a hydrogen embrittlement, it does not have a hydrogen embrittlement as such, and then that is why we say the post necking region during a tensile testing, because when do for the testing we really required some sort of a testing to the load this component under tensile stress, and then when it is not charged with the hydrogen, or hydrogen exposure is not there, we are able to see the cup cone shape, and then the SEM we are able to see really micro image, we say that there are micro voids in this, which is a typical ductile failure, which has been already mentioned in one of the previous lecture. So, they really develop MCV, and then there is the characteristics of the ductile failure. So, that is why A and B has been shown on the normal high cycle fatigue phenomena, which has happened in this case. While coming to the second case, where this specimen was subjected to hydrogen charging, and temperature was kept at a very low, is a 45, sorry, and then the temperature was kept at around 45 degree. However, the failure we are able to see is kind of a shear failure at the 45 degree angle as such. And now these are the failures, and then we are also able to find out the many more failures of pits and maybe the fractures, and then in the elongation of the many cracks also. So, this is a completely brittle failure. Now, when I look at the SEM image, we find still there are dimples available, small dimples available, but most of the time is the kind of the brittle failure. We are able to find out the bridges, we are able to find out this striations in the surface also, and then that is why we say that there are many quasi cleavage macro instead of micro one, we are able to find out the macro voids. There is not very small, but we are able to also find out the secondary cracks, not only the primary cracks, but the secondary cracks. And another one is important thing is the intergranular cracking, that means very low stress, the low load, but the material has gone under significant reduction in strength. That is why this is happening. We find intergranular cracking, and both the figures in this case has been shown in the 1 mm level at the kind of micro level, and this has been shown as a 10 micron level, kind of magnified by 100 times, and then we are able to find out this kind of problems because of the hydrogen embrittlement, and many times it has been tested that results are much faster. Now, where we mentioned about that this everything is happening at the normal temperature or lower temperature, but we also know the activities will increase significantly when the temperature or thermal heat is available. Now, thermal heat can be outside environment or maybe internal mechanism. I use a word initially, the friction force. The friction force is on the higher side. Naturally, we require more energy to move the component or provide relative motion between two components. Now, this energy has been given, but this energy has been used and getting converted to heat. Then there is a possibility of increasing the temperature also, or there is a possibility of the thermal cycle. Maybe temperature is varying around 0 to 50 degree or 50 to 100 degree or 100 to 150 degree, something like that, because of the change in environment, or maybe because of loading, unloading, and the temperature is changing that way. So, this is when the temperature changes, naturally the thermal cycle starts, and if the thermal cycle is associated with any of the oxidation, corrosion, hydrogen embrittlement, value will be much more, and that is why the slide is being shown to you. Basically, here the one case studies was done on the turbine blades, and the reference has been given. This reference has come from 2016, it was published in the 2016, and then we say the thermal mechanical fatigue investigation of one superalloy, and this superalloy has been used generally for the turbine blades. Now, here the title has been given something like a temperature assisted oxidation, and what is really the temperature assisted oxidation is something like that. We are very happy that the top surface will be in the subject and will be forming the oxide layer, but in this case where the presence of oxygen, presence of temperature makes much on the higher level, the dimension of the oxide layer, and then causes a more problem. And if there is a fatigue loading, naturally it will cause a much more severe damage to the surface. So in this case they have kept a two temperature condition, one is a 500 to 1000 degree, that means variation is happening, right. So cyclic variation in this case it has been kept lower than 500, and then they found that particularly life cycle becomes a half. If the temperature is increasing to some level, temperature the life cycle is reduced. In this case, naturally the life cycle of this is something like a 4675 maybe number of cycles, and this is just half. So what is really the difference is coming? They are able to find out still some sort of a ductile failure. Their secondary cracks they are able to see, and then they are able to see the striation something like this, and that has been shown in this case as a fatigue striation as such. But while coming to this one, they find more on when the ridges are happening, and there is a more possibility of fracture, and that this is the expansion of this portion only has been zoomed in this manner, while in this case this portion has been zoomed in this manner. So when the temperature increases, fatigue life comes down significantly, material property also get deteriorated, and then we are able to find out with increase in a material. First question comes, so increase in a material should make a material more soft, more ductile. Well, that does not happen when there is a thermal cycling, and this increased temperature, lower temperature, increased temperature, lower temperature, and that is really causing a kind of the fatigue, which is a more on the fracture side or maybe the brittle sides. So we say there is a strong dependence between temperature, oxidation and fatigue life. Increase in a temperature, increase in oxidation environment causes a reduction in a fatigue life. So we can say high temperature the oxidation degrades, and then not only this, this also shows there are numerous cracks at the sites. So the dissociation, there are more possibilities there. When go for high temperature, more and more cracks get formed, and then the pieces maybe the material which is very kind of superalloy material will get disintegrated, will have a much shorter life compared to its expected life when there is a temperature assisted oxidation or temperature assisted corrosion or temperature assisted hydrogen inbuilt in mine. So many environmental factor they work with each other, or maybe they become supportive of each other, and we need to really think in that direction. So this is my last slide. Thank you for your attention.